In this video, we're going to talk about data quality and reliability, or basically how much you can trust your data and how much information you can get from it. So why does quality data matter? It matters because the data that you have from your experiment is the evidence that you have to support your conclusion. So if your data isn't strong and it's not high quality, then you can't be sure that your conclusion is valid. So whatever you're trying to learn as a scientist, the better data you have, the more sure you can be that what you're learning is actually true. So you want to make sure that you have the highest quality data possible. So there are a couple features of high quality data that you want to make sure you have when you're doing your experiment. The first is that there should be lots of it. You should have a lot of data points. This is why it's a minimum requirement that everyone has at least 20 points of data for your project, because the more data you have, the more you know about the relationship between your variables. Second, your data should be consistent, meaning it should follow a clear trend or pattern. And the more scattered or random your data is, the more difficult it can be to really get a clear relationship and have a solid understanding of how your variables connect to each other. Lastly, your data shouldn't have any outliers. Now, an outlier is one data point, or like 1 to 3 data points that don't fit the pattern. So it's a point that is outside of the pattern of what the rest of the data points are doing. So ideally, you should have very few or no outliers in your data, and it will be of higher quality. So let's look at a few examples. In these two graphs, I have my graph on the left, which has only 3 data points, and then my graph on the right, which has many, many more data points. And you can see that in the graph on the right, it's really easy to tell that there's a direct relationship, which means that as I go from left to right, I'm increasing in the y-axis, so I'm going up as I go from left to right. And it's clear that it also follows a linear pattern, because it pretty much looks like a straight line. In this graph on the left, you can't even really tell what the relationship is. It just looks like this weird triangle. It goes up first and then back down, and it's really difficult to tell what's actually happening. So the more data points you have, the better information you will get, and the more information you will have to tell you what the relationship is between your two variables. So in these next examples, we're going to talk about variability in data. And the basic rule of thumb is that the more precise your data is, the more reliable it can be to tell you about the relationship between your variables. So in these graphs, my graph on the left has a trend line, but the data points are really far spread out from the line and kind of form a cloud around it. Whereas in my graph on the right, all the data points are pretty close to the line, which is telling me that I can say with greater certainty that there is a linear direct pattern from the graph on the right that I can from the graph on the left. Because if I'm going like from one data point to the next, I'm up, I'm down, I'm up, I'm down, I'm jumping around so much that it's kind of fuzzy and less reliable. But in this graph, I'm so close to the trend line that it's a lot easier to say that there's a linear relationship between the variables here. So the more precise your data is, the stronger your conclusion will be about the relationship between your variables. So now I'll give you an example of what an outlier looks like. So as I briefly mentioned earlier, outliers refer to the data points that just don't fit into the pattern. So if I'm looking at my graph, I can see that for the most part, I have an upward linear trend. So I have a direct relationship because as x is going up, y is also increasing. But I have a few data points that are just really outside this pattern and don't follow it. And overall, I still have a linear direct relationship, but these points are deviating from that pattern, and that's why they're called outliers. And as much as we would like to just throw out the outliers and just say that they don't really matter and that our pattern is still just linear, you can't just throw them out. They're still part of your data, and they're often interesting to talk about and can help you add more to your lab report by trying to explain what happened and why the outlier occurred in the first place. And it can also help you out with your analysis and conclusion because it can give you a jumping off point to talk about random error, which is one of the ways that you can get a higher score on those steps of the project. One approach that you could take to incorporate the outlier into your data is to calculate an average of your trials with the outlier and without the outlier and discuss them both. And you can talk about how much the outlier is throwing off your data, or what the difference is between what your data would be if everything fit the pattern and then your data with the outliers that you had. So let's look at one more example here. In this graph, it's telling me how the hours that students studied affected the grades that they received. And so as we get into discussing this data set, I'll be talking about what the strengths are and what the weaknesses are. So let's start with strengths. The axes are clearly labeled. It's very evident that the x-axis is the hours studied by students and the y-axis is the grade that they received. Second, there are a lot of data points and it's enough to clearly establish a relationship. Even though it's not exactly defined, whether it's linear or exponential, because I don't have like a perfect straight line here, I do know that it's a direct relationship. So it's very obvious that overall, as the hours studied goes up, the grade that students received goes up as well. So it's enough to clearly tell me that it's a direct relationship in my data. Next, there are no outliers in this data set. And this might surprise you because you might look at this and say, oh, it doesn't clearly establish a linear pattern or an exponential pattern. It's kind of jumping around from one point to the next. But all of the data points are within this like cloud or fuzzy patch of data here. If I had a point like all the way out here or all the way up here, that would be a very clear outlier. But here, even though my data isn't 100% precise, there aren't any outliers. So now let's talk a little bit about the weaknesses. As I've already said a little bit, the data varies from point to point and doesn't create a truly straight or curved line. So even though I know that it's a direct relationship, that it's going up as I go from left to right, I can't really say whether it's an exact straight line or an exact curved line because of the fact that the data is fuzzy and forms a cloud rather than just a very specific and precise pattern. So that's it for this video. I hope that this has given you a little bit of information that you can use to evaluate the quality of your own data and determine how much you can trust the data that you gathered to tell you about the relationship between your variables in your experiment.